classification. There are some technical properties of the aggregate. The first one, we can know something about the properties of a questionnaire. Four kinds of states. The first one is the oven dry. Oven dry means there is no moisture in the pores of aggregates. And then in the air dry means the moisture in the pores of aggregate is equal to the atmosphere. And then the saturated and surface dry. Saturated and surface dry. And last one is after the rain, we can get the wet state of the aggregates. So, and for the aggregate strength, we must get this aggregate crashing index. If this value is bigger, it means, if this value is bigger, it means there are not all aggregates crash during the experiment. So if this value is bigger, it means it's big. If this value is big, it means the strength of the aggregate is bad. It's poor. It's poor. Strength of it is poor. And then the soundness, and particle shape of surface feature. Particle shape will be maybe there are four kinds of particle shapes. The first one is round. The second one is angular or subangular. And then the needle and flake. The needle and flake shape of the aggregate is harmful for the concrete. Harmful for the concrete. So if we want to evaluate the performance, if we want to evaluate the quantity, quality of the aggregate, we can use the percentage or the content of the needle and flake shape. If the needle and the flake, if the content of the needle and the flake is big, it means the quality of the aggregate is poor. And then for the surface feature, we can get a smooth or roughness. So last time, there are four kinds of aggregates. The first one is a natural aggregate, such as the powder, and the second one is the crushed stone. Manufactured aggregate. For this one, the shape is round. Yeah. For this one, the shape is round, and for this one, the shape is angular. And for this one, the surface is smooth, but for this one, the smooth is roughness. So if we use these two kinds of aggregates to produce the concrete, maybe the different performance is different. So here's the first one is the work ability. We have learned what is the work ability. It means it's easy for us to mix, transport, and construct the concrete. So there are two kinds of aggregates. Which one is better for the workability of the concrete? Which one? The first one? Yeah. The second one? Which one? The first one. The first one, yes. For this one, the workability is very good. But for the strength of concrete, which one is better? The second one. The second one. So this is the difference for the particle shape and the particle surface. Performance of concrete. Okay.
I missed what you said during the particle shape. You said that if it's poor, I missed what you said during the particle shape.
particle shape.
If the aggregate is poor, meaning the shape is what? If it's poor,
If the article you mean if the article is poor,
yes.
what does this mean?
Yes, which shape is for poor aggregate?
Which is good for the aggregate? You mean there are 4 kinds of particle shape.
Yes.
Which one is good for the particle shape?
Yes.
Yeah, this is 2. This 2.
Triangular.
This 2 is good. Okay, this 2 is bad, and they are harmful. These 2 they are harmful for the concrete. Okay, the flake, the needle shape and the flake shape of the aggregate is harmful for the concrete.
What is it so?
Huh?
What is it?
What? You want to know the reason? Yes, I have. Last time I have to explain for you. Okay, maybe someone don't know what is the reason they are poor. If this is the specimen, this is the wrong. This is the wrong shape of aggregate. It is good. And this is a needle shape of aggregate. So maybe in the same specimen, there are 2 kinds of aggregate shape. If we put the load, conduct the load on the specimen, the strain will occurs in the specimen. And when the load is small, at the same load, which one will be broken at first? Which one? The needle one. Yeah. If this particle broken, correct will occurs. Correct will occur. We can get the cracks in the specimen. And then if we increase the load, the cracks will develop. So the stress of concrete will be decreased. So the needle shape and the flake shape is helpful for the concrete, especially for the strings. And we also learn some impurities. Impurities, that is the clay and the compound. So what is it? The impurities. The impurities always means that they are harmful. Yes, they are harmful to the concrete. Why? For example, for the clay or the clod. For the clay or the clod. For the clay or the clod, they will affect the bond between the cement paste and the aggregate. Because I have also explained last time. If this article is very clean, it is very clean, and then the cement paste can contact with the surface of the aggregate, tightening. Yeah, contact it, tightening, bond it, tightening. But if there was some dust, such as the clay or the cloud, on the surface of the aggregate, the bond between the cement paste and aggregate is affected. Just like this one. Okay, this is the aggregate, but this aggregate is very clean, so there are no dust on the surface. And this is the cement paste. When they contact it, the bond is very good. The bond is very good. And this is another aggregate, but there are some dust, impurities. There are some dust on the surface. So the cement paste contact with the aggregate. The bond will be like this, not this. So this one, that one. Which one is good? This one. Yeah, this one is good. This one. Because the bond area is big, and the space is big. But like this one, just like dotted. So the space it's cool. It's really cool. And then, such as like the organic substance, sulfate, or sulfate and chloride, they all can react with the stable paste. So it is harmful. They are harmful. For the gradation, what do we have learned? What is important for us? It is about the safe analysis. The purpose of the safe analysis is to get the gradation. Gradation. To get the gradation of the aggregates, because we have learned that when we use the aggregate in the concrete, the aggregate must have some gradation. So when we could get this kind of, maybe there are about 70 kind of safe. And then when we put the aggregates into it, and after the vibrating, we can get on each side. Maybe there are some aggregates on it. So we'll need to get 3 kinds of index for the gradation. 3 kinds of index. 3 kinds of index. The first one is the individual percentage retent. The individual percentage retent, if the mass of the aggregate on the same one is M1, the individual percentage retent A1 is M1. What is this mass?
Initial mass.
The total mass. The total mass. This is the unstable one, the mass unstable one. And this is the total mass of the aggregate. The total mass of the aggregate. This is the individual percentage retent. The first index was gradation. Okay. For this one, A3 means M3. Okay, this is individual percentage retent. The second one we call it what? Accumulative percentage. For the accumulative percentage retent, it means the individual percentage retent at this stage and up, down, up, or down.
No.
For the accumulative percentage retent, it means the individual percentage retent at this stage and above this stage or beyond this stage. Yeah. Okay. Because there are no states above it. There are no states above it. So then this one is equal to this one. But for the third state, it is the individual percentage retent at this state and this state and this state. Okay?
Please repeat, Washington. Please repeat.
Repeat? Okay. Are you clear about this one?
Yes.
Maybe confused by this one.
The last part, that is it.
Another point. It means the accumulative means what? Means 1 plus 1 plus 1. Yes? So, for the accumulative percentage return, it is the individual percentage return at this, sorry, the third, yeah? At this thing, and above, yeah, above this thing. So, above the third is the second and the first. But for the first one, there is no thing above it. So, this one is equal to this one. Okay? And then, the third index for the gradation is the passing percentage. Passing percentage. The passing percentage what? The passing percentage means the particles passed the third stage, past the third stage. But the amount of this is the accumulative percentage return. So it is equal to 100. This is for the third kind of index. The first one is the individual percentage return. Second one is the accumulative percentage return. The third one is the passing percentage. We can. This one is the most useful for us. This one is most useful because we can after the same analysis we can decide how many aggregates at each stage. Yeah, we can get how many saves at each stage. So after the same analysis, we can get the gradation of the aggregates. How to express the gradation? We can use this kind of curves. This is the gradation curve. So there are four kinds of, especially there are two kinds of typical curves, gradation curves, two typical gradation curves. The first one is that continuous graded aggregate. The second one is a gap graded. So the first one is a continuous graded. The second one is a gap graded. So I want to ask you a question. What is the difference for these two curves? It means what? The difference means what? What is the difference? Maybe we can know this is the dot line, this is the solid line. But except this one. What is the difference for these two curves? What is the difference for these two curves? One is a continuous grade. Second one is a gap grade. Gap grade. How can I get this continuous curve? How can we get this continuous curve? It means what? For the smallest size, it gets the smallest percentage. It gets the smallest passing percentage. And then, when the size increase, we can find that the passing percentage increase. And how it increase? Continuously increase. Yeah? Continuous. Maybe this one is 4%, 5%, maybe 7%, and 11%, and maybe 16%, maybe 24%. Yeah, they increase continuously. Right here, they increase continuously. Okay, from this diagram, if the percentage increase continuously, it means what? It means what? If the passing percentage increase continuously, it means what? Look at this diagram.
Yeah.
It means what?
A1 is A1 quantity is big.
It means what? It means at each stage there must be aggregates. Yes?
Just aggregates or like they're supposed to be
Yes.
equal.
It means there are some aggregates on every stage. On every stage. Because if there is no stage, no aggregate, I mean, the passing percentage of one, the passing percentage of two, they are the same. If they are the same, it means what? Like this one. Yeah? Like this one. It's the gap grading. What is gap grading? Okay, for the first part of the curve, it is also the continuous grading. But we find that the passing percentage of 5 millimeter is the same with 10 millimeter. Yeah? So they are very close, very close. Yes? Or even the same. Even the same. So what does this mean? It means what? Okay, if this is 16, this is 10, this is 5. From this is 50. 15 and 5, okay? This the passing percentage of 15 is the same 10 and 5. So it means what? Is there aggregates at this stage? No. Is there aggregate at this stage?
Yes.
Yes or no?
Yes.
They are the same. The passing percentage of 15 is the same with 5. Yeah? They are the same. Yeah? Maybe about 36 or 37. Yeah? 36 or 37. They are the same. So, there is no aggregate at here. There is no aggregate at here. Yeah. So what is the gap gradient? Gap gradient means there is no aggregate at 1 or 2 or more states. Yeah? And then from this aggregate, from this gradation curve, can you find the percentage of aggregate on each state? Can you find it? Can you find it? Can you find from this continuous gradient curve, can you find the content of aggregate on each thing? Okay. This is for the 0.08. The passing percentage is about 4%. Yeah, 4%. And for the for the 0.16, the passing percentage is about 5. So this is 4, this is 5. It means what? This is 5. The passing percentage of this side is 4. For this one is 5. It means what? It means what? It means between these two sizes, how many percent of aggregate? 1. Yeah, again. This is 4%. This is 5%. It increased 1%. Yeah, this 1% is means the aggregate between 0.08 and 0.16 between these two sides is 1%. It means on the same, on which side the amount of the aggregate is 1%. On which side? On this one or on this one? 1%. On this one or on this one?
0.16.
On this one. On this one. That okay. Okay, and next one. This is for this day, the passing percentage is 4%. Yeah, at this curve. And for this day, the passing percentage is 5%. Yeah. So it means there is 1% of aggregate at this stage. Yes? 1%. 1%. And then we can we can find on every side, on every thing, how many aggregates on it. It is different. It can be calculated by the passing percentage, but it is different to the passing percentage. If the passing percentage of this thing is 4%, we cannot conclude that the amount of this size is 4%. Not 4%. This 4% is the amount below this thing. And this is about, and for the another two curve is dense grade. Dense grade means what? Dense grade means the passing percentage of the fine aggregate. What is the fine aggregate? It means the size is small. Yes, the size is small. For these small sizes of aggregate, the passing percentage is high. It means the fine aggregate, the amount of the fine aggregate is big. The amount of the fine aggregate is big. So it is a dense grade aggregate. But for this one, we can find that. There is no fine aggregate. Yeah. For the size below 2.5, there is no aggregate. So it means the open graded aggregate. These are the four kinds of typical curve of aggregates. Four kinds of typical aggregate. But these two is most typical. Most typical. But the gap graded aggregate means an aggregate in which one or more intermediate size, one or more intermediate sizes are missing. They are missing. And for the dense grade aggregate, it means an aggregate with a particle size distribution that results in the least voids or lowest void content. This is for this dense graded aggregate. And for the open grade aggregate, it means an aggregate with a particle size distribution that results in relatively large voids. This is the small. This is the lower. This is the lower void, but this one for the large voids. Large voids. So that is for the what we have learned about the gradation. And for the how to evaluate the values of the aggregate, maybe we can divide them into two parts. The first one is the fineness modulus of fine aggregates, and another one is for the coarse aggregate. The fineness modulus is this, like this. It refers to the composite fineness, especially for the fine aggregate of the sand. Because the sand is belong to the fine aggregate with different diameters. The diameter means the size. So for fine aggregates used in acid mixture and for fine aggregates used in semi-concrete, the formula of fineness modulus is different, but there are some similarity between them. Okay, when we calculate the fineness modulus, what kind of value we need to use? What is this one? A 0.615. A 0.6. It is what? What we have learned just now. It refers to what? What we have learned just now. Yeah. Accumulative percentage return. Accumulative percentage. So this index is the gradation index. It is called the accumulative percentage return. So after the stable analysis, we can get the gradation of this aggregate, and also we can use the accumulative percentage return to calculate the fineness modulus of the aggregate, fine aggregate, So after the calculation, we can get the fineness modulus. It's just some number. So for the different number of the fineness modulus, we can find the different types of sand. If the fineness modulus is between 3.1 to 3.7, we call this sand as coarse sand. Coarse sand means what? Means that size of this sand or fine aggregate is big, coarse aggregate. And then if the fineness modulus is between 2.3 to 3. We call it the medium side. Medium side. And for the fineness modulus between 1.6 and 2.2, we call it the fine side. Fine side. And then if the fineness modulus is below 1.5, we call it the super fine side. Super fine side. Super fine. Okay, from this table we can calculate that. Calculate what? Calculate what? The fineness modulus is bigger. Means the aggregate is closer. It's closer. This value is bigger means the fineness means the aggregate is closer. So it's closer. And then if we use different kinds of aggregate for the concrete, what are the influence? For example, if I select this coarse sand to produce concrete, cement concrete, and then we choose that I chose another fine sand. This is the coarse sand. This is the coarse sand, and this is the fine sand for the concrete. What is the influence? If the aggregate, if the fineness of the aggregate is big, it means the aggregate is coarse. Yeah, that is what. And if the fineness of the aggregate is small, it means the coarse belongs to the fine aggregate. Fine aggregate. So if we use this fine sand, we use this fine sand for the same mass of coarse sand and fine sand, the specific surface of the fine sand is bigger. Okay, maybe like this one. This is one sand particle, a sand particle. Okay, this is a sand particle. Okay, look at this blackboard. This is the sand particle, and then I broke it. Maybe
Smaller.
40 small particles. I broke it. Okay. This is one particle, but the size is big, and then I broke it into 14 small particles. For this one particle, there is a surface of it. Yeah, this is the area. And when the cement paste mixed with the aggregates, the cement paste must bond at the surface of the aggregate. Yes?
Yes.
And when this one particle broken into 14 small particles, for each small particle, it has a surface.
Yes.
And when we
Put them together.
get them together, so which surface? 1, 2. Which surface is bigger? The second one. Yeah. The second one. The surface of for these 14 small particles is bigger. What does this mean? What does it mean? It means when we use the cement paste to bond the aggregate, the surface of the aggregates is increased. Yeah, the surface because the surface of these 14 small particles is bigger than this one big particles. Yeah. So the surface is increased. The surface increased. The cement paste needed to wrap that is also increased. Is also. I mean what? Okay, just for this particle, maybe I just need 1 kilogram cement paste. But the surface of this 14 smaller particle is bigger than it. So maybe I need 1.5 or even 2 kilogram cement paste because the area is bigger. So the cement paste needed to wrap it is also increased. So for the field construction, we always likely to use if other performance is satisfied with the requirements, we was likely to use some cost side to decrease because the amount of cement paste is increased. It means what? It means we need to use a lot. We need to use much more cement and water, especially the cement, because in the cement concrete, the cost of cement is the most expensive. It's the most expensive. So we're likely to use some coarse fine aggregate to decrease the amount of cement paste. Okay, great. Mm-hmm.
Can you send us this PPT?
Oh, what I have to get them more to the office.
You have sent for me.
Yes, I have
It's right now. I went there, but they didn't.
Okay. That's so thanks.
Yeah, I asked why.
Means please.
Yeah, it's plan.
I have gave them all.
What happened? This subject and I don't know. Next month is over us. And just he wanted to collect. No, not anything. Just they wanted collect. Yeah, this is collect. Actually, they need this people for not for us. You can send us.
Okay. Okay, I ask you. I have your chair. I have your chair.
No.
Yeah, I have your chair. Yes.
I forget your
Okay. Okay, I'll send it to you. All that.
and I will.
Okay. Okay. Let's continue. We have just learned how to evaluate the fineness of the fine aggregate. But for the coarse aggregate, how to evaluate the fineness of it? We can use the maximum size of coarse aggregate. For the maximum size of coarse aggregate, what is the maximum size of coarse aggregate? Okay. From this diagram, maybe okay. Look at the black box. After the save analysis, okay, we can decide the maximum size of the coarse aggregate. It means, what is the maximum size of coarse aggregate? It means the smaller list say opening through which the entire sample pass, entire aggregates pass. So, from this diagram, which one is the maximum size? Maybe this is 14. 14, 16, 10. Which one is the maximum size of the coarse aggregate? Which size? Which size? Which size is the maximum size of this aggregate? 20? Okay. There is no aggregate in here. Yes? It means all particles, all aggregates pass through this stage.
Yes.
But for 15, it's also all passed. Yes? They're also all passed. But it is smaller than this one. Means the smallest thing. So although there are 3 states all passing, but this one is the smallest state. So what is the maximum size of this aggregate? What is the maximum size? 15. Yes, 15. Okay? And then the nominal maximum size. What is the nominal maximum size? Means the smallest state opening through which most 95% of the particle size. So, which one is the nominal maximum size? Maybe it's 15. But we need to look at the percentage of this. If the mass at here, if the mass of aggregate at this stage is 10% or 15%, if the mass of the aggregate at here is 15%, which one is the nominal maximum size? 10 or 15? Which size? Which size is the nominal maximum size? If the mass of aggregate at here is 15. How many? Which one? It's 15. Yes? But if the mass of aggregate at here is 3%, which size is the nominal maximum size? Which one? Which one? You need to look at 95%. 95% means what? Means the mass above this size is below 5%. Yes? Because 95% passing, 5% return. Yeah? And if the return is 3%, which one is the nominal maximum size? 10. Yeah, 10. If the mass at here is bigger than 5%, if the mass at here is bigger than 5%, so the nominal maximum size is 15. But if the mass at here is below 5%, the nominal maximum size is 10. The maximum is 10. Okay.
You actually, from the previous diagram, from the previous graph, this coming from the natural from the first diagram, this one, these curves.
This one? Yes. Yes, we can find the maximum size of course aggregate here. Okay? So for example, for this curve, which size is the maximum size of it? Which one? Yeah? This one. And for this one, we cannot find it. Yeah? But for this one, we can find it. The maximum size is 40. Yeah? And for the coarse aggregate we used in the structure, maybe there are, for the maximum size of it is controlled by this standard. Okay? According to the structure standard, if the section, the maximum size of coarse aggregate is below 1/4 minimum size of section. If this is the structure, maybe this is the section. The maximum size of coarse aggregate is we can divide them into 4 parts. The maximum size of the coarse aggregate is smaller than this. Is smaller than this. And then for the steel aggregate, maybe we need many steel bars. And this is the volume. This is the distance between the bars. The coarse aggregate we can use the maximum size of it must below here. Or it cannot go through. And then for the solid floor, the thickness is 1.2. So What is the differences between the gradation and fine modulus or fine aggregates? Okay. There are lots of differences between them. And have sand A and sand B, which have the same modulus. Do I have the same gradation? If the modulus is the same for these two sands, A and B, if the modulus, fine modulus is the same, do they get the same gradation? No, it doesn't. So this part may be it's difficult. This part may be difficult. I just explain it. Okay. For the gradation, because what we have learned toward us, if we want to use the aggregate for the concrete, the gradation of the aggregate is very important. The gradation of the aggregate is very important. So how can we get the gradation of the aggregate? What kind of gradation is good for the concrete? What kind of gradation is bad for the concrete? Maybe we need to learn something about the gradation theory. For the first theory is the flow theory. For flow theory, it means the solid particles. Solid particles means the aggregates. Solid particles means the aggregates. The solid particles can be constituted with the maximum loss density and the minimum void content. So if we put the aggregates together, there are two requirements we need to satisfy. The first one, we need to get the maximum density. Because for the structural material, the density is bigger, it always means the strength is bigger. And then the minimum void content. The minimum void content means a high density. So, and the more the gradation curve close to the parabola. Do you know what is a parabola? Parabola? What is parabola? What is parabola? I mean, like this one? Yeah. This is a parabola. If the gradation curve is like this one, it means it is the best. That means the best. So this is the formula for the parabola. It means the percentage. This is the passing percentage. This is the passing percentage of each size. This I means the size. The size of the aggregate. This is the passing percentage of each grade and this is a constant. K is a constant, and this one is the size. Is the size, particle size of it. So from this formula, the first thing we need to get the constant. What is the constant? Okay, this is the formula for the Fineness area. Okay, we can find that if the curve, how can we get this curve? If we want to get this curve for the next aggregate, we need to divide it. We need to divide the aggregates on each side. For example, if I want to use the aggregate, the size of the aggregate is between 40% to the smallest this size. How can we get this? We need to get 14 sides, and then 36.5, 30.5, and so on. For each one, we need to get this. But it is difficult for us. For this kind of aggregates we always divided them into 4 kinds. But for this kind of aggregates, maybe it has 3 kind of sides. So it is difficult for us to get the gradation, the best gradation. So how can we solve it? We need to the type diagram. Type solving means we can explain the gradation curve from one single curve to a range. If I put these 2 kinds of aggregates together, make them the mixed curve is like this. The curve is like this. But if we want to get this curve, it is very, very difficult. But we can get this curve. Maybe 2 kinds of aggregates I need. Maybe 3 kinds of aggregates I need, or 4. We can use this kind of method to decide the proportion of each aggregate. Okay. Suppose there are 2 circles. Basically, a particle size taking an advantage in every kind of aggregate, and the particles of this size in the other aggregates quite low. What does this mean? It means this. We can divide the aggregates into 4 kinds aggregates. The size of each aggregate is different. So we can find the advantage particle size. For example, 30. 30 is between 20 and 40. So the size of 30 millimeter is the particles of 30 millimeter is mainly come from what? Come from what? Huh? The 30 millimeter aggregates is mainly come from where?
From A.
A. Yes. And the maybe 2.36, 2.36 millimeter aggregates mainly come from D. This is the advantage. This is called this is so-called advantage size. Okay. Example. Maybe three kinds of aggregate. Three kinds of aggregate. There are three kinds of aggregate. A, B, C. Okay, A, B, C. Maybe there are two proposed. The first one is we can propose the content of A. The content of A is X. And the content of B is Y. The content of C is Z. Z. So when we mix them together, X plus Y plus Z, how many? X plus Y plus Z, how many?
100.
100. Yes, 100. And then maybe this one is difficult. It's difficult. When they mix together, we can get each kind of size. For example, for the size of maybe 15, okay, for the size of 15 and 15. For the size of 15 in mixer, put them together. For the size of for the size of 15 size, it comes from three parts. The first one is come from A, but the content of 15 in A is very little, even though. And then the 15 come from B. Its many come from B. And then come from C. But the content of 15 in C is very little, or even low. But in A, this size, the content of this size in A is this one. And this is the content of A. Plus this one, plus this size in B, and the content of B, and C, and this size in C, and it contains the content of C. Just like this. We can get this one. This is in the mixer. When we mix them together, when we mix these three kinds of aggregate together, this is the content of this size. The content of this size is come from three parts. So for the we can look at this formula. Okay. Firstly, we can find a size, advantage size. For example, 13. Okay, the size of 13 millimeter. 13 millimeter. The 13 millimeter, we can find that there is no 13 millimeter at here. There is no 13 size at here. So the size of 13 is mainly come from A. This one is 0. Yeah, because there is no 13 micrometer. This is 0. This is 0. So this is 0. This is 0. We can find X. X means the content of A. Yes, we can get the content of A like this. And then we can find another size. This size may be 4.6. 4.75. 4.75 is many come from C. So this one is 0. This one is 0. This one is 0. Just this one. We can decide Z. We can do Z. And when we get X and get Z, how can we get Y? How can we get I? Y is 100. Yes? So we can decide the content of each kind of aggregate. But when we use this percentage, we must check and adjust. Must check and adjust. This is the mathematical method for the proportion design for proportionals. And then another method to decide the content of each aggregate is the graphic method. Graphic method also means the revised balanced area method. So the most common use, this is the most commonly used graphic method, quite convenient for mixing more than 3 aggregates. Okay, what we have learned is the mathematical method, but if the types of aggregate is above 3, just like 4, 5, it is difficult. We can use this graphic method. For the graphic method, firstly we need to establish the coordinate system. For the coordinate system, okay, this is a rectangle, and then we can get, this is the passing percentage. The passing percentage is from 0 to 100. So how can we get the same opening size? Same opening size. The same opening size we need to use the gradation medium. This is the gradation limits. It has an upper limits and lower limit upper limits and low limits. And then we can calculate the medium of them. And then we can get the coordinates. This is the size distributed on the coordinate. Where is the 75? 75 is here. This is the size of 5 millimeter. This is the size of 5 millimeter. And 60 is at here. 60 is for the 2.5 millimeter size. And 45, this is 45. 45 is for the 1.2. And 35 is for 0.63. And 24.5 is for the 0. So for each size, we can decide the place. We can decide the site of the sizes here. And then, because there are 4 kinds of aggregates, so we can draw the gradation of each one. And then from here we also can find the size of these 4 kinds of these 4 aggregates. For example, for the gradation for the aggregate A, the size of aggregate A is between 2.5 and 15
millimeter. This is for gradation A, for aggregate A. And for aggregate B, the size is between, maybe this is 1.2 to 5 millimeter, to 5 millimeter. And for 3, for aggregate 3 is maybe 2.3, 0.3 to 1.2, 1.2. So when we draw the gradations for each aggregate, and then we can decide the content of each aggregate. When we draw this line and make the distance between here is equal to between here. These two gradation lines. And then this line will contact with this solid line. We can get that this is the proportion of aggregate A. This is the proportion of aggregate A. And then we can find for this, for aggregate B and aggregate C, the minimum size of aggregate B is 1.2. But for the maximum size of aggregate C, the maximum size is 1.2. So we can just connect it. And then there is a dot we can get right here. And this is for proportion of B. For proportion of B. For proportion of A, what is the proportion of A? We can line it right here. Maybe just 65. 65. If this is if this is 65, what is the proportion of A? 65 or 35? 65 or 35? 35. Yes, 35. 35. And then for the aggregate B, this is 65, and this is maybe 36. 65, 36. Maybe 29. Between them. 29 between them. And then for aggregate B and aggregate C and aggregate D, they are depart. We can find their line to divide them into two parts. And then it will contact with this. This is about maybe say 36. This is 16. 36 is maybe the proportion of C is about 20%. 20%. And then the return 60 is for aggregate D. Aggregate D. Okay, this method is some complicated. Maybe we can close it. So this is what we have learned today. And especially for the technical property of the aggregates and including the physical properties and including the chemical properties of the aggregates. And we have learned something about the gradation, and how to decide it, how to get the proportion of the aggregates. This is the mixed design. Gradation, the aggregate mixed design. So this is what we need to learn today. So today class is over. Okay.